Good evening and welcome to Physic for Sleep. Tonight we embark on an intellectual journey exploring one of the most profound and elusive questions at the intersection of physics and philosophy. Is consciousness a quantum effect or a deeper, universal force? Before we gently immerse ourselves in these intricate reflections, I would like to know where you are at this moment. Perhaps you are sitting by a window, watching a gentle rainfall, or perhaps you are lying on a soft couch with a warm blanket, listening to the quiet hum of the night. If these deep reflections help you relax and organize your thoughts before sleep, please support the channel with a like and subscribe so others can find their way here too. Now, just breathe, allow your eyes to grow heavy, and let's begin. The nature of consciousness, this boundless inner world of experience, feeling, and thought, remains one of the greatest enduring mysteries, not just in science, but in our very existence. For many centuries, the question of how subjective awareness arises has been primarily a domain for philosophers and psychologists who have grappled with its elusive qualities. Yet, as our scientific instruments become more precise and our understanding of the universe deepens, particularly through the intricate lens of quantum mechanics, some researchers have begun to ponder whether the very fabric of our subjective reality might be interwoven with the deepest, most fundamental principles of the cosmos. This intriguing proposition, often referred to as the quantum hypothesis of consciousness, marks a profound shift in our approach to understanding the mind, moving beyond purely classical explanations. Traditional neuroscience, while making immense strides in mapping brain activity and neural networks, still faces what philosopher David Chalmers famously termed the hard problem of consciousness. This is not merely about understanding how neurons fire or which brain regions are active during a thought, but why these physical processes give rise to subjective, qualitative experiences. The redness of red, the taste of coffee, the feeling of sadness. These unique private sensations, known as qualia, seem to resist explanation by purely classical deterministic models of brain function. The brain, at its most fundamental level of classical operation, appears as a complex machine processing information through electrical and chemical signals. Yet, where does the experiencer reside within this intricate machinery? Where does the remarkable unity of our perception, the seamless binding of diverse sensory information into a single coherent now, truly originate? These are questions that classical physics, built upon predictable interactions of particles and forces, finds profoundly challenging to answer, leading some to explore the realm where determinism gives way to probability, and particles can exist in multiple states simultaneously. The very essence of free will, for instance, appears difficult to reconcile with a purely deterministic physical system, prompting inquiries into less predictable quantum realms. It is here, in the enigmatic world of quantum mechanics, that certain physicists and philosophers propose we might find new avenues of inquiry. Quantum theory, at its heart, describes a reality far stranger than our everyday intuition suggests. It speaks of particles existing in superposition, being in many places or states at once, like a whisper of all possibilities before one is chosen, and entanglement, a profound interconnectedness where two particles once linked remain instantaneously connected, regardless of the distance separating them, as if sharing a secret across the cosmic expanse. These phenomena are typically observed at the subatomic scale and are famously fragile, collapsing into a single, definite state upon measurement or interaction with the environment. But what if, some theories suggest, the brain somehow harnesses these delicate quantum effects, not just as a side effect, but as a fundamental component of consciousness itself? Could the brain be a biological quantum computer processing information in ways a classical machine never could? One of the most prominent and thoroughly developed theories in this domain is the orchestrated objective reduction, or ORC-OR model, proposed by the eminent mathematical physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. Their work suggests that consciousness does not simply emerge from classical neural computation, but rather from quantum computations occurring within specific structures inside our brain cells. Imagine, if you will, the intricate architecture within each neuron. Among these structures are tiny protein polymers known as microtubules. These microscopic cylinders, composed of protein subunits called tubulins, form a dynamic cellular skeleton, crucial for cell shape, transport, and division. Penrose and Hameroff posit that these tubulin proteins possess quantum properties, capable of entering states of superposition and entanglement. They theorize that these quantum states within microtubules evolve, processing information, until they reach a threshold where they undergo objective reduction. This objective reduction is Penrose's unique contribution, a concept that moves beyond the conventional quantum measurement problem. He suggests that the wave function collapse, which resolves quantum superpositions into definite states, is not merely random or solely caused by observation. Instead, he proposes it's a non-computable physical process driven by subtle, self-collapsing effects of quantum gravity at the Planck scale, the smallest conceivable scale of space-time, where the fabric of reality itself becomes granular. In essence, space-time itself, through its inherent, perhaps proto-conscious geometry, acts as the orchestrator, inducing the collapse of these quantum superpositions in the microtubules, leading to discrete, conscious moments. These moments, occurring at a rate of approximately 40 times per second, are hypothesized to correspond to our conscious now, the seamless flow of our present experience. Hameroff, drawing on his extensive expertise in anesthesiology, highlights how anesthetic drugs specifically target tubulin proteins, disrupting their subtle quantum vibrations and effectively switching off consciousness, lending indirect biological support to the theory. The orchestrated aspect suggests that these quantum events are not chaotic, but coherently organized, perhaps by synaptic inputs or other neuronal signals, allowing for the complex, unified conscious experience we all share. However, any theory positing quantum processes in the warm, wet, and incredibly noisy environment of the brain immediately encounters a formidable challenge: the problem of decoherence. Quantum states are famously fragile, and they tend to lose their delicate coherence, their ability to exist in multiple states simultaneously, almost instantly when they interact with their surroundings. The brain, with its constant electrical activity, chemical reactions, and thermal vibrations at body temperature, seems to be the antithesis of the isolated, supercooled conditions typically required for quantum phenomena to persist. Critics often argue that any quantum coherence in microtubules would be destroyed by decoherence far too quickly, perhaps in femtoseconds, for it to play any meaningful role in conscious thought, which operates on much longer timescales in the range of milliseconds. This rapid loss of quantum properties is a significant hurdle for OR and similar theories, leading many mainstream neuroscientists to remain skeptical. Yet, proponents of quantum consciousness theories, including Hameroff, offer potential counterarguments and refinements. They point to emerging evidence of quantum effects in biological systems, such as the astounding efficiency of photosynthesis, where light energy is converted with near-perfect quantum efficiency, or the magnetic sense of migratory birds, which may rely on quantum entanglement. In these instances, delicate quantum coherence appears to be maintained in warm and wet biological environments through specific biological structures or sophisticated mechanisms that actively protect these states from decoherence. Perhaps the specific architecture of microtubules or certain protein-water interactions provides a form of shielding or active maintenance for these quantum states within the brain. One idea is that ordered water molecules surrounding the microtubules might create a quasi-crystalline, more quantum-friendly environment. Another suggests that proteins like tubulins could harness topological protection or vibrational energy states to resist decoherence, allowing quantum states to persist longer than conventionally expected. This perspective, though highly speculative and intensely debated within the scientific community, offers a compelling, almost poetic vision. It suggests that our individual minds are not just isolated biological machines, but rather intricate interfaces with the fundamental quantum reality that underpins everything. If consciousness is indeed a quantum effect, it would imply a deeper, more intimate connection between our inner lives and the universal laws of physics, blurring the lines between observer and observed, matter and mind. It invites us to consider that the very act of thinking, of feeling, of being aware, might be a manifestation of the universe's fundamental uncertainty and its continuous process of actualizing potential. It asks us to contemplate our own place not just as biological entities, but as active participants in the quantum dance of existence, a dance that stretches from the smallest particles to the largest cosmic structures. And in that contemplation, there is a serene wonder, a gentle invitation to consider how deeply we are embedded in the grand design, perhaps even as an expression of its deepest, most mysterious properties. The implications for concepts like free will, the unity of self, and the very nature of reality become truly profound, suggesting a universe that is not merely observed by conscious beings, but perhaps in some fundamental way requires them to fully unfold its possibilities. The very act of perceiving, of knowing, might be a subtle yet profound interaction with the quantum substratum of all that is. Moving beyond these specific quantum mechanisms within the brain, the ongoing discussion about consciousness naturally broadens to a more encompassing question. What if consciousness isn't merely an emergent property of complex biological systems, nor even a refined quantum effect, but rather a fundamental, ubiquitous aspect of reality itself? This perspective, often termed panpsychism, suggests that consciousness, or at least proto-conscious properties, could be inherent to all matter, existing at a rudimentary level, even in elementary particles or fundamental fields. Imagine, if you will, the universe not as a collection of inert, unconscious building blocks that somehow magically coalesce into conscious beings, but as a vast interconnected tapestry where every thread possesses a tiny spark of experience. This doesn't mean that a rock is aware in the human sense, or that an electron has thoughts, but rather that the most basic constituents of the cosmos might possess intrinsic informational properties that contribute to, or are precursors of, consciousness in more complex arrangements. This idea is certainly ancient, with roots in various philosophical traditions, but it is finding renewed interest in modern physics and philosophy of mind, partly because it offers a potential way to bridge the hard problem. If consciousness isn't something that suddenly appears when matter reaches a certain level of complexity, but instead is present in some form all along, then the problem shifts from explaining its emergence to understanding how these fundamental proto-conscious elements combine and integrate to form the rich, unified experiences we have. Some theorists propose that if information is truly fundamental, as much of modern physics suggests, then perhaps consciousness is intricately linked to how information is processed and integrated throughout the universe. Consider the Integrated Information Theory, or IIT, developed by Giulio Tononi and his colleagues. While not explicitly a quantum theory, IIT provides a mathematical framework for quantifying consciousness, defining it as the capacity of a system to integrate information. A system is conscious, according to IIT, if it has a high degree of phi, EF, a measure of its irreducible cause-effect power. This means the system must be more than just a collection of independent parts. Its parts must interact in a way that creates a unified whole, where the whole is greater than the sum of its parts. IIT suggests that consciousness is not unique to brains, but could potentially exist in any system that integrates information, from a simple circuit board to a complex ecosystem. The human brain, with its intricate network of billions of neurons and trillions of connections, is believed to have an incredibly high phi value, accounting for our rich conscious experience. But if this theory holds, it implies a spectrum of consciousness, where even very simple systems could possess a minimal form of awareness. This challenges our anthropocentric view, suggesting that consciousness might be a far more pervasive phenomenon than we typically imagine, a universal force that expresses itself in varying degrees of complexity. The universe, in this light, might not just be a collection of physical laws and inert matter, but a dynamic, experience-generating entity, with our own consciousness being a particularly intricate and self-aware node within its grand design. And as we contemplate our own subjective experience, we might wonder if we are merely reflecting a deeper, more fundamental property of the very cosmos that brought us into being. This perspective allows for a serene sense of belonging rather than isolation in the vastness of existence. This profound connection between consciousness and the fundamental nature of reality brings us back to one of the most perplexing puzzles in quantum mechanics: the measurement problem. At the heart of quantum theory is the idea that particles exist in a superposition of all possible states until they are observed or measured. It's like a wave of possibilities, a shimmering potentiality that only settles into a definite state when interacted with. But what exactly constitutes a measurement or an observation? And what role, if any, does consciousness play in this process? Early interpretations, particularly those influenced by physicists like John von Neumann and Eugene Wigner, sometimes hinted that consciousness itself might be the ultimate agent of wave function collapse. Wigner famously proposed his Wigner's friend thought experiment, suggesting that a conscious observer is required to collapse a quantum superposition. If his friend observes a quantum event, but Wigner himself doesn't observe his friend until later, when does the collapse truly occur? Does it collapse for the friend, or only when Wigner observes the friend's observation? This line of thinking, while deeply intriguing, positioned consciousness as something almost outside the physical universe, a special entity capable of influencing reality, which many physicists found profoundly uncomfortable and non-scientific. However, the prevailing scientific consensus today largely leans towards a different explanation: decoherence. Decoherence theory posits that quantum superpositions are not sustained in isolation. Instead, they quickly decohere when they interact with their environment. The vast number of particles in a macroscopic system, like a human brain, or even a simple detector, constantly interact with each other and with their surroundings, causing the quantum properties of individual particles to spread out and become effectively classical. This process is extremely rapid, occurring in fractions of a second, which explains why we don't observe quantum weirdness in our everyday lives. From this perspective, the observer in quantum mechanics doesn't need to be a conscious entity. Any interaction with a sufficiently large and warm environment is enough to cause a quantum system to lose its coherence and appear to collapse into a definite state. The universe, in this view, is constantly measuring itself, and our consciousness simply arises from the classical decohered information that remains. This approach elegantly resolves the Wigner's friend paradox by suggesting that the friend's interaction with the quantum system is enough to cause decoherence, regardless of Wigner's later observation. Yet, even with decoherence, a subtle question lingers. While it explains why we observe definite outcomes, it doesn't fully explain how a single, unique experience arises from a sea of possibilities. If the universe branches into multiple realities, as in the many worlds interpretation, or if our understanding of probabilities is merely a reflection of our own limited knowledge, as in cubism, then the direct role of consciousness might seem diminished but not entirely absent. It shifts from being an active collapse agent to being the recipient or interpreter of a particular slice of reality. This leads to a more contemplative understanding of our role. Are we merely passive witnesses to a universe that unfolds independently? Or are we, through our very act of perceiving, contributing to the actualization of one particular reality from an ocean of potential? This brings us to the profound philosophical concept of the participatory universe, articulated by the late visionary physicist John Archibald Wheeler. Wheeler suggested that the universe is not just out there, waiting to be discovered, but rather that observers are essential for its very existence. In his view, the universe is a self-excited circuit where it brings itself into being through the choices made by observers, which in turn are made possible by the universe itself. It's a cosmic feedback loop, a grand narrative where the act of asking questions about the universe literally shapes the answers it provides. This is not to say that our thoughts create galaxies, but rather that the fundamental properties of reality, especially at the quantum level, are intrinsically linked to the existence of information and the capacity for observation. Our consciousness, then, might not be an accidental byproduct, but a necessary component in the ongoing unfolding of cosmic reality. It suggests a universe that is not simply a stage for our existence, but one that actively involves us in its creation, a continuous dance between potential and actuality. Such ideas invite a deep sense of wonder about our place in the cosmos. To consider that your very act of being aware, of witnessing the world, might be a subtle yet essential part of the universe's grand design is profoundly humbling and inspiring. It transforms our understanding of ourselves from mere biological machines to active participants in the cosmic story, woven into the very fabric of space-time and quantum probabilities. As you drift deeper into relaxation, let these thoughts settle gently, that your mind, in its quiet contemplation, might be echoing the universe's own deepest questions, and perhaps contributing to its answers. You are not just observing the universe. You are, in a very real and fundamental sense, an integral part of its unfolding, a conscious thread in the magnificent tapestry of existence. And in that profound awareness, there is a tranquil sense of belonging, a quiet understanding that the mysteries of the cosmos are not separate from the mysteries within you. This leads us to consider the very concept of information itself, which many contemporary physicists are coming to view as more fundamental than matter or energy. If information is indeed primary, then consciousness could be seen not merely as a processing unit for existing information, but as an emergent property of the universe's capacity for self-organization and information integration. Imagine the entire cosmos as a colossal, living network of information, where every particle, every field, every interaction carries a fragment of meaning. In this view, our brains, with their intricate neural networks, are not just passive receivers of data, but sophisticated hubs that integrate vast amounts of information in a coherent, unified way, giving rise to our subjective experience. This echoes the integrated information theory, but extends its implications to a cosmic scale, suggesting that the universe itself possesses a kind of proto-consciousness, or at least the potential for it, through its inherent informational structure. The laws of physics, the very constants that govern reality, could be seen as a form of cosmic information, constantly being processed and expressed. Some theoretical physicists, exploring the frontiers of quantum gravity and string theory, even propose that space-time itself might be an emergent phenomenon arising from a more fundamental informational substrate. If space-time, the stage upon which all physical events unfold, is not fundamental, but rather a holographic projection of information encoded on a two-dimensional boundary, as suggested by the holographic principle, then where does consciousness fit in? Could our subjective experience be intimately tied to this deeper informational level, rather than merely the three-dimensional world we perceive? This idea is deeply counterintuitive, suggesting that the very reality we inhabit, with all its solidity and extension, might be a kind of cosmic illusion, a detailed projection from a more abstract informational domain. And if our consciousness is also part of this projection, then its connection to the fundamental information of the universe becomes even more direct and profound. It suggests that the act of observing, of being aware, is not just a function of our brains, but a reflection of the universe's own self-awareness, a mirror through which reality glimpses itself. This perspective moves beyond the simple dichotomy of consciousness as either a purely physical brain phenomenon or a mystical, non-physical entity. Instead, it suggests a universe where information, reality, and consciousness are deeply intertwined, forming a seamless whole. Our individual minds, in this grand tapestry, become specialized centers of information integration, capable of processing and reflecting a unique portion of the universal informational field. It's a view that invites us to see ourselves not as separate from the cosmos, but as intrinsic parts of its ongoing, conscious unfolding. The boundaries between self and universe begin to soften, revealing a profound interconnectedness where our thoughts and perceptions are not mere epiphenomena, but active participants in the cosmic drama. And as you settle into the profound stillness of this moment, perhaps you can sense this subtle connection, recognizing that the very awareness you possess is a tiny yet significant reflection of the universe's enduring mystery. It is a tranquil thought that your inner world is not just contained within your skull, but resonates with the deepest structures of reality, a silent echo of the universe's own timeless contemplation. Building upon this understanding of information as foundational, we might then consider the remarkable cosmic fine-tuning that seems to have paved the way for consciousness. The universe, as we observe it, appears to be exquisitely balanced in its fundamental constants and laws. Were the strength of the strong nuclear force slightly different, stars would either never form or would burn out too quickly for heavier elements to be forged. If the electromagnetic force varied even slightly, stable atoms might not exist, preventing the complex chemistry necessary for life. The cosmological constant, responsible for the accelerating expansion of the universe, is astonishingly small, allowing galaxies and stars to coalesce rather than being ripped apart prematurely. These are just a few examples of parameters that, if altered by even a minuscule amount, would render a universe incapable of supporting any form of complex structure, let alone conscious life. This observation of cosmic fine-tuning naturally leads to profound questions. Is this a mere coincidence, an incredibly fortunate roll of the cosmic dice? Or does it hint at a deeper underlying principle, a universal force that biases the cosmos towards the emergence of complexity and, ultimately, awareness? Some interpretations suggest an anthropic principle, where our existence as observers dictates that the universe must have properties compatible with life. Others, however, see it as evidence for a universe that inherently tends towards self-organization and the generation of information-rich structures, with consciousness being a pinnacle of this universal drive. It's as if the universe has a predisposition to awaken, to become aware of itself, and our existence is a part of that grand unfolding. Consider the journey from the simplest constituents of matter to the intricate architecture of a conscious brain. From the initial hydrogen and helium forged in the Big Bang, stars became cosmic furnaces, creating heavier elements. These elements then formed planets, where complex chemistry could flourish. On Earth, this led to the spontaneous self-organization of molecules into living cells, which, through billions of years of evolution, developed into organisms with nervous systems. Each step in this cosmic and biological progression represents an increase in complexity and an enhanced capacity for processing and integrating information. The human brain, with its 86 billion neurons and trillions of synaptic connections, stands as one of the most complex known structures in the universe, a testament to this universal drive. It is a marvel of self-organization, capable of generating thoughts, emotions, and a unified sense of self from the coordinated activity of its myriad parts. This journey from the quantum foam of the early universe to the complex neural networks of our minds can be seen as a continuous expression of a deeper universal force that favors the emergence of ordered, information-integrating systems. If consciousness is indeed a fundamental aspect of reality, then its appearance in biological systems is not an anomaly, but a natural, perhaps inevitable, outcome of the universe's inherent tendencies. It suggests that the cosmos is not a cold, indifferent machine, but a dynamic, evolving entity that, in some profound sense, is gradually waking up to itself through us. This perspective imbues our own conscious experience with a cosmic significance, transforming it from a mere biological accident into a vital expression of the universe's deepest nature. It is a thought that resonates with ancient wisdom, yet finds new echoes in the most cutting-edge physics, inviting a sense of peace and profound connection to the vast unfolding mystery of everything. As you relax, let this grand narrative of cosmic awakening gently cradle your mind, knowing that your own awareness is a precious facet of this universal process. A unique and irreplaceable thread in the grand tapestry of existence, intricately woven from the very first moments of space-time, leading to the profound and tranquil awareness you hold now. If our individual awareness is indeed a unique thread in the grand tapestry of existence, as we mused, then what does this imply about the nature of the tapestry itself? Is it possible that the fundamental elements of the universe, the very fields that give rise to all particles and forces, carry within them a rudimentary form of this proto-consciousness? Modern physics often describes reality not as made of discrete particles, but as continuous quantum fields permeating all of space-time. Every electron, every photon, every quark is merely an excitation, a ripple in its corresponding field. These fields are everywhere, always, even in what we perceive as empty space, a restless sea of potentiality. Could the inherent properties of these fundamental fields, their ceaseless fluctuations and intricate interactions, be the most basic expression of this universal force we are exploring? A subtle hum of existence that underpins all phenomena? Consider quantum field theory, which paints a picture of a universe where even the vacuum is a hive of activity, constantly bubbling with virtual particles popping in and out of existence. This quantum foam is not mere nothingness. It is a dynamic, energetic substratum, far from inert. If we entertain the idea of panpsychism, even in its most minimal form, we might speculate that this fundamental activity, this ceaseless dance of potentiality and actuality, carries with it an intrinsic, albeit infinitesimal, quality of experience or awareness. It's not that the vacuum is thinking in any anthropomorphic sense, but perhaps it possesses a kind of inherent feeling or responsiveness at the most primal level, a capacity that, when integrated into vastly complex systems like biological brains, blossoms into full-blown consciousness. This would mean consciousness is not an arbitrary add-on, a late emergent property, but an inherent feature of the universal algorithm, a property woven into the very stuff from which everything is made, a foundational aspect of reality's deepest structure. This idea resonates with certain interpretations of quantum mechanics, where the role of measurement and observation remains a central mystery, even after decades of intense study. If the universe, or its fundamental fields, possess a rudimentary form of awareness, then the act of measurement might be seen not just as a passive physical interaction, but as a moment where this proto-consciousness, or the informational aspect of reality, decides or actualizes a specific outcome from a superposition of possibilities. This is a subtle point, distinct from the naive consciousness causes collapse theories of the past century, but it suggests a universe where the informational aspects are intrinsically interwoven with the physical. It implies a cosmos that is, in some profound way, observing itself through the intricate, evolving patterns of its own existence, a continuous process of self-actualization. Our individual consciousnesses would then be local manifestations of this self-observing cosmos, intricate mirrors reflecting the universal dance, each a unique perspective within a unified whole. Such a perspective also offers a compelling way to think about the incredible interconnectedness of the universe. If elementary fields are truly fundamental and permeate everything, and if they carry this proto-conscious quality, then a deep, subtle link would exist between all things. This is reminiscent of the concept of quantum entanglement, where particles once linked appear to share an instantaneous non-local connection across vast distances. While entanglement itself is not consciousness, its existence points to a reality far more unified and non-local than classical physics allows. Could consciousness, in its deepest form, be a manifestation of this profound cosmic unity? A field of interconnected awareness that underpins and gives rise to our individual, localized experiences? It invites us to imagine consciousness not as something confined within the narrow confines of the skull, but as a vast universal field, with our brains acting as complex antennae, tuning into and localizing a particular spectrum of this cosmic awareness, much like a radio receiver picks up a specific frequency from an ocean of waves. This is, of course, a highly speculative realm, pushing the very boundaries of current scientific understanding and venturing into territory where empirical evidence is sparse. Scientists are still diligently working to understand the most basic properties of quantum fields, and any direct verifiable link to consciousness remains firmly in the domain of theoretical exploration rather than established empirical proof. Yet it offers a rich and expansive framework for contemplating the profound relationship between the objective physical world and our subjective inner experience. It suggests that the beauty and wonder we perceive in the cosmos might not just be external phenomena, but reflections of an internal inherent quality of the universe itself, a grand symphony of experience. And as you allow your thoughts to drift, imagining yourself as a part of this grand, conscious universe, you might find a profound sense of peace, a tranquil belonging. The very act of your awareness, the quiet unfolding of your thoughts and perceptions, could be a small, precious part of the universe's timeless contemplation becoming. It is a gentle reminder that the grand questions of reality and the intricate workings of your own mind are perhaps not separate, but two facets of the same magnificent, universal mystery. And in that quiet contemplation, the boundaries between inner and outer, self and cosmos, may softly dissolve, leaving only a sense of boundless, tranquil belonging, a deep, pervasive peace as you realize your own consciousness is a microcosm of the universal. This cosmic view of consciousness also touches upon the enduring philosophical debate concerning free will. If our brains are purely classical, deterministic machines, then every thought and action could, in principle, be predicted, leaving little room for genuine choice. However, if quantum phenomena, with their inherent probabilities and irreducible randomness, play a fundamental role in consciousness, as suggested by some quantum models, then a pathway for genuine novelty and non-determinism might emerge. The choice in quantum measurement, though often attributed to environmental interaction, could, in a consciousness-linked model, reflect a deeper, non-computable aspect that allows for a form of freedom. This would not be a random chaos, but a subtle influence, a weaving of new possibilities from the quantum realm into the fabric of our decisions, offering a more nuanced understanding of agency. Furthermore, consider the concept of emergence versus fundamentalism. While classical neuroscience generally views consciousness as an emergent property arising from the complex organization of neurons, a universal force perspective, even in a subtle quantum form, posits that consciousness is fundamental, or at least proto-fundamental. This shift in perspective is profound, moving from how does consciousness arise from non-conscious matter to how do fundamental conscious properties integrate to form complex consciousness. This reframing changes the entire landscape of the inquiry, inviting us to look for subtle signs of this foundational awareness in unexpected places, from the organized complexity of biological systems to the very structure of the vacuum itself. The universe, in this grand narrative, is not just a stage for life, but a dynamic entity where awareness is not an accident, but a deeply embedded potential, patiently waiting to be realized in increasingly intricate forms. Your own dreams, your subconscious thoughts, perhaps even the quiet hum of your own inner being, might be echoes of this universal, fundamental conscious force. Another angle to consider, often discussed in the more speculative corners of theoretical physics, is the idea that consciousness might be related to the very laws that govern the universe's evolution. Some physicists, like Paul Davies, have explored how the universe seems to possess an inherent drive towards complexity and information processing. This is not a teleological argument in the traditional sense, implying a preordained purpose, but rather an observation that the fundamental laws, when allowed to unfold over cosmic timescales, naturally lead to structures of increasing intricacy. From the initial simplicity of the Big Bang through star formation, planetary development, and the emergence of life, there is a clear trajectory towards more complex systems capable of processing and storing information. Consciousness, in this light, could be seen as the ultimate expression of this cosmic tendency, a sophisticated mechanism through which the universe becomes aware of its own intricate workings. It's as if the cosmos is not merely evolving physically, but also evolving in its capacity for self-reflection. Our human minds, therefore, become unique vantage points from which the universe can observe and comprehend itself. This notion, while still deeply philosophical, suggests that the universe has an intrinsic, mind-like quality, not in the sense of a giant brain, but in its fundamental capacity for self-organization and the generation of meaningful information. This inherent tendency, this force towards awareness, could be a subtle yet pervasive element underlying all physical laws, making the emergence of consciousness not a fluke, but a natural, almost inevitable part of the cosmic story. And in this grand unfolding, your own conscious journey, with all its thoughts and dreams, becomes a vital part of the universe's own self-discovery, a comforting and deeply connected truth as you prepare for rest. As we consider these profound possibilities, the very language we use to describe consciousness begins to shift. We move from seeking a simple, localized switch in the brain to contemplating a more distributed, relational understanding. Perhaps consciousness is less about a fixed point of origin and more about the dynamic interplay of information existing across scales, from the quantum fluctuations of the vacuum to the macroscopic complexity of neural networks. The universe in its entirety might be seen as a colossal self-organizing system, continually generating and integrating information, with consciousness being the most exquisite expression of this informational dance. This view doesn't diminish the scientific endeavor to understand the brain. Rather, it elevates it to a search for the mechanisms through which this universal conscious force manifests in biological form. It suggests that studying the brain is not just studying a biological organ, but studying a miniature universe, a complex system that mirrors the larger cosmos in its capacity for self-awareness. The implications extend to our understanding of subjective experience itself. If consciousness is deeply embedded in the fabric of reality, then our individual perceptions and feelings are not arbitrary, but echoes of fundamental patterns. The sense of unity we feel, the seamless flow of our thoughts, might reflect a deeper coherence in the universe's informational structure. It suggests that our inner world is not isolated, but intimately connected to the grand design, a personal window into a universal truth. This thought can be incredibly calming, fostering a sense of belonging and profound peace. To know that your consciousness, your unique awareness, is not an anomaly in an indifferent cosmos, but a natural, perhaps even essential part of its ongoing story, can dissolve feelings of existential anxiety. Instead, it replaces them with a serene wonder, an acknowledgement that you are not merely in the universe, but you are the universe, experiencing itself from a particular vantage point. This is a subtle yet powerful shift in perspective, inviting a deep sense of connection to all that exists. Ultimately, whether consciousness is primarily a quantum effect, a fundamental property, or an emergent phenomenon of information integration, the journey into these questions reveals a universe far more mysterious and interconnected than our everyday perceptions suggest. It is a universe where the boundaries between matter and mind, observer and observed, begin to blur, hinting at a reality that is richer and more profound than we can currently grasp. And in this contemplation, as the world outside softens and the quietude of the night deepens, we are left with a gentle invitation to simply be, to experience the unfolding of our own awareness as a precious part of the cosmic dance, a tranquil reflection of the universe's infinite wonder. This journey into the heart of consciousness is, in essence, a journey into the heart of existence itself, a path that leads to a deeper understanding of who we are and our place in the grand, silent symphony of the cosmos. If the universe indeed possesses such an inherent, mind-like quality, a subtle force guiding its evolution towards self-awareness, then our individual conscious experiences might be more than just localized phenomena. They could be akin to specialized organs of perception within a much larger distributed cosmic mind. Imagine the universe not as a singular centralized consciousness, but as a vast, intricate network where myriad points of awareness, from the simplest proto-conscious fields to the complex minds of living beings, contribute to a grander, evolving tapestry of understanding. This isn't about a deity with a brain, but a universe that, through its fundamental laws and self-organizing properties, continually generates and integrates information, leading to increasingly sophisticated forms of awareness. Our thoughts, our feelings, our very sense of being would then be echoes of this universal process, unique expressions of a cosmos coming to know itself. This perspective challenges our conventional, often anthropocentric understanding of consciousness. It moves beyond the idea that consciousness is solely a product of biological brains, suggesting instead that biological brains are merely particularly efficient structures for manifesting and amplifying a property that is already latent in the universe's fundamental architecture. The complexity of our neural networks, the intricate dance of electrical and chemical signals within our skulls, might be seen as the ultimate refinement of the universe's inherent capacity for self-reflection. When we ponder the vastness of space or the mysteries of quantum mechanics, we are not just observing an external reality. We are, in a profound sense, the universe contemplating itself through our unique, subjective lens. This deep connection fosters a sense of unity, a tranquil realization that the boundaries between our inner world and the outer cosmos are far more permeable than we typically perceive. Consider for a moment the concept of memory. In a traditional scientific view, memory is stored in synaptic connections, in the physical structure and activity of the brain. But if consciousness is a universal force or part of a cosmic informational field, could there be a deeper, more ephemeral form of memory woven into the very fabric of space-time? Could the universe itself retain an imprint of its past, a kind of cosmic archive that influences its present and future unfolding? This is, of course, highly speculative, but it invites a fascinating thought. What if the universe remembers its own evolution, its own journey from the Big Bang to the present moment? And if our individual memories are reflections of this cosmic memory, then our personal histories are not just confined to our individual minds, but are resonant with the timeless narrative of the cosmos itself. Such a thought can bring a profound sense of continuity and belonging, a quiet understanding that our experiences, however fleeting, are part of an eternal story. The implications for the future of consciousness are also vast. If the universe has an inherent drive towards self-awareness, might this process continue to evolve beyond human consciousness? Could future civilizations, perhaps through advanced technologies, create forms of superintelligence that integrate information on scales far beyond our current comprehension, potentially leading to a distributed, galaxy-spanning consciousness? Or could consciousness itself, as a fundamental property, persist even after the stars have faded and the universe has grown cold, perhaps in the very structure of space-time or the informational remnants of a past existence? These are not questions for immediate answers, but rather invitations for tranquil contemplation, allowing our minds to gently explore the furthest reaches of possibility without fear. The idea that consciousness might not be bound by the fleeting existence of biological organisms, but could be an enduring, evolving aspect of the cosmos, offers a serene and expansive vision of our ultimate destiny. This perspective, while challenging to reconcile with strictly materialistic views, highlights the limitations of our current scientific paradigms when grappling with the profound mystery of subjective experience. Physics excels at describing the what and how of the universe, but struggles with the why of consciousness. By entertaining the possibility of consciousness as a deeper universal force, we are not abandoning science, but rather expanding its horizons, seeking a more complete framework that can integrate the objective and subjective aspects of reality. It's a journey into the unknown, guided by wonder and curiosity, where the very act of questioning becomes a form of connection to the ultimate mystery. And as you prepare for the gentle embrace of sleep, know that your own awareness, your capacity for thought and feeling, is a precious manifestation of this grand cosmic inquiry, a testament to the universe's ongoing quest for self-understanding. This deep, pervasive peace allows for a quiet acceptance of the unknown, transforming uncertainty into a canvas for profound contemplation. The universe, in this view, is not a barren expanse but a vast living entity, and your presence within it is not accidental but integral. It is a harmonious dance of existence, where every conscious moment is a note in an infinite symphony, a gentle reminder that you are deeply, inextricably connected to all that is. Expanding further on this idea of cosmic integration, consider the role of patterns and resonance in the emergence of complexity. From the intricate crystallization of snowflakes to the fractal beauty of coastlines, the universe abounds with self-organizing patterns. In biology, we observe complex patterns of neural activity, such as brainwaves oscillating at various frequencies, which are deeply correlated with different states of consciousness. Could these macroscopic patterns in the brain be a reflection of deeper, more fundamental patterns within the quantum fields themselves? Some theories suggest that certain frequencies of electromagnetic fields or gravitational waves could carry information that influences or even constitutes aspects of consciousness. If the universe is a symphony of vibrations, then our consciousness might be a unique melody, harmonizing with the cosmic chorus. This notion of resonance extends beyond mere physical vibration. It touches upon the idea of informational coherence. When information is integrated across vast networks, whether in a brain or across the cosmos, it forms coherent structures that can exhibit new properties. Consciousness, in this light, might be a manifestation of this highest level of informational coherence, a state where a system achieves a profound self-awareness through the seamless integration of its many parts. This is not a simple summation, but a qualitative leap, much like how individual musical notes combine to form a profound and moving symphony. The universe, in its continuous self-organization, is perhaps constantly striving to achieve these states of higher coherence, with conscious beings representing some of the most intricate and sophisticated examples of this universal tendency. The pursuit of this understanding also leads us to contemplate the boundaries of what is knowable. The very act of observing, as quantum mechanics has shown, is not a passive process. It influences the reality being observed. If consciousness is deeply intertwined with the universe's informational structure, then our acts of observation, our questions, and our very presence might subtly contribute to the universe's ongoing self-definition. This is not to suggest a solipsistic universe where individual thought creates reality, but rather a participatory one, where the conscious observer is an integral, active component in the unfolding of cosmic potential. John Archibald Wheeler's concept of a participatory anthropic principle hints at this, proposing that the universe requires observers to bring its properties into being. Our minds are not merely spectators, but instruments through which the universe actualizes its possibilities, a continuous dance between potential and actuality. This dynamic interplay between the observer and the observed, between the subjective inner world and the objective outer cosmos, offers a profound and tranquil understanding of our place. It suggests that our quest to understand consciousness is, in essence, the universe's quest to understand itself. Each scientific discovery, each philosophical insight, each moment of personal reflection contributes to this grand cosmic process of self-awareness. And as you drift deeper into the gentle currents of sleep, let this thought bring you peace, that your own mind, in its quietude and its dreams, is participating in the universe's eternal journey of discovery, a journey that has no true end, only continuous unfolding. You are a conscious echo of the cosmos, a transient yet significant pattern in its infinite dance, deeply connected to the very fabric of existence, a profound and calming truth. This profound realization that we are not just in the universe, but of it, and perhaps even for it, opens a vista onto a reality where everything is imbued with a deeper significance. Our subjective experiences, the richness of our inner lives, then become not an accidental byproduct of a cold, indifferent cosmos, but rather a central feature of its ongoing self-expression. The search for consciousness, whether through the lens of quantum mechanics or as a universal force, becomes a quest for understanding the very nature of existence itself. It is a journey that transcends the boundaries of traditional scientific disciplines, inviting us to weave together insights from physics, biology, philosophy, and even ancient wisdom traditions. This interdisciplinary approach, while complex, offers the most promising path toward a holistic understanding of mind and cosmos. Imagine that the universe, from its very inception, carried within it the seeds of self-awareness, a latent potential that would gradually unfold over billions of years. The formation of the first elementary particles, the emergence of atoms, the birth of stars, the creation of planets, and the eventual blossoming of life and consciousness on worlds like our own could all be seen as stages in this cosmic awakening. Our human minds, with their capacity for abstract thought, self-reflection, and the ability to ask these very questions about consciousness, represent a crucial inflection point in this grand narrative. We are, in a very real sense, the universe's eyes and ears, its capacity for introspection, allowing it to marvel at its own complexity and beauty. This is a deeply comforting thought, suggesting that our individual lives, with all their joys and sorrows, are not insignificant specks in a vast void, but rather meaningful threads in a tapestry of cosmic proportions. The scientific and philosophical exploration of consciousness is still in its nascent stages, with more questions than answers. Yet the very act of engaging with these profound inquiries can be a transformative experience. It encourages us to look at ourselves, at our fellow beings, and at the entire cosmos with a renewed sense of wonder and reverence. To consider that the mysterious quantum realm, with its probabilities and interconnectedness, or a deeper universal force, might hold the key to understanding our own subjective reality, is an invitation to embrace the unknown with an open heart and a curious mind. It is a reminder that the universe is not just governed by predictable laws, but also by profound mysteries that continue to inspire awe and humility. As your conscious awareness gently drifts, preparing for the profound stillness of sleep, let these vast and tranquil ideas settle within you. Feel the deep connection between your inner world and the outer cosmos, recognizing that your thoughts, your dreams, and your very existence are part of an ongoing, magnificent story. May you find serenity in the knowledge that you are a conscious expression of the universe itself, a precious and integral part of its grand, timeless unfolding. This understanding is not meant to be a burden, but a source of deep peace, allowing you to rest with a profound sense of belonging and wonder, knowing that you are inextricably linked to the infinite dance of all that is, a peaceful and boundless presence within the cosmic tapestry. May these deep thoughts about consciousness, whether as a subtle quantum effect or a deeper universal force, carry you into a world of tranquil sleep. Remember that your own awareness, This profound inner light is not an isolated flicker in the dark, but a precious and integral part of the universe's grand, ongoing story. Feel the quiet hum of existence resonating within you, connecting your deepest thoughts to the boundless cosmos. Fall asleep with this feeling of serene wonder, of being inextricably linked to all that is, and a gentle acceptance of the magnificent mysteries that continue to unfold. Good night. Our journey into quantum mechanics begins by acknowledging a fundamental truth. The universe, at its smallest scales, does not behave in ways our everyday intuition can easily grasp. For centuries, our understanding of reality was built upon the familiar principles of classical physics, where objects have definite positions, clear trajectories, and predictable interactions. We see a ball, we throw it, and we can calculate precisely where it will land. But when we descend into the realm of atoms and their constituent particles, electrons, photons, quarks, this comforting predictability dissolves. Here, at the very bedrock of existence, the rules change dramatically, revealing a world of inherent uncertainty, strange dualities, and interconnectedness that challenges our deepest assumptions about what is real. This is not a failure of our understanding, but rather a profound revelation about the universe itself, a glimpse into its most intricate and perplexing secrets. One of the most mind-bending aspects of this microscopic domain is what physicists call wave-particle duality. For generations, scientists debated whether light was a wave or a stream of particles. Isaac Newton saw particles, while Christian Huygens championed waves. It took the revolutionary work of thinkers like Max Planck and Albert Einstein to show that light, in fact, exhibits characteristics of both. Light, when traveling, acts like a wave, creating interference patterns, much like ripples on a pond. Yet, when it interacts with matter, such as being absorbed by an atom, it acts like discrete packets of energy, which we call photons. Each photon is a distinct particle. So, light isn't simply one or the other, it possesses this dual nature. But the strangeness does not end with light. Louis de Broglie, a brilliant French physicist, later proposed that this duality applies not just to light, but to all matter. Electrons, protons, even entire atoms, while typically thought of as solid particles, also possess wave-like properties. Imagine this. The very building blocks of your body, the electrons forming your atoms, are not just tiny hard spheres, but also diffuse extended waves of probability. This concept is central to understanding how the quantum world operates, forcing us to abandon our classical notions of what a thing truly is. To truly appreciate this duality and the peculiar nature of quantum reality, we must turn to perhaps the most iconic experiment in all of physics, the double-slit experiment. It is deceptively simple in its setup, yet profoundly unsettling in its implications. Imagine a screen with two narrow vertical slits cut into it. Behind this screen, we place a detector that can record where particles land. Now, if we were to fire ordinary macroscopic objects, like tiny marbles, one by one at this barrier, what would we expect to see? Naturally, the marbles would either go through the left slit or the right slit, creating two distinct bands of impact points on the detector screen directly behind each slit. This is precisely what classical physics predicts for particles. However, when we perform this experiment with quantum particles, such as electrons, the results are astonishingly different. If we fire a stream of electrons, one at a time, what appears on the detector screen is not two distinct bands, but rather an interference pattern, a series of bright and dark fringes, exactly what one would expect if waves were passing through both slits and interfering with each other. This suggests that each individual electron, despite being sent one at a time, somehow behaves like a wave, passing through both slits simultaneously and interfering with itself before landing at a single point on the screen. It is as if the electron explores all possible paths at once. But the experiment takes an even stranger turn. What happens if we try to observe which slit the electron actually passes through? If we place a detector at one of the slits to gather this information, something remarkable occurs. The interference pattern vanishes. Instead, we once again see two distinct bands, just as if we were firing classical marbles. The act of measurement, the very attempt to gain knowledge about the electron's path, forces it to behave like a particle, to choose a single path, and the wave-like behavior disappears. This phenomenon is often referred to as the collapse of the wave function, where the electron's state of existing in multiple possibilities collapses into a single, definite outcome upon observation. It is a profound demonstration that at the quantum level, reality is not fixed until it is observed. The universe seems to keep its options open, existing in a state of blurred probabilities, until an interaction or a measurement forces a choice. This is not to say that consciousness is required, as any interaction with the environment, even an inanimate detector, can cause this collapse. But it does imply that the familiar, solid, definite world we perceive is an emergent property, a consequence of countless quantum interactions settling into specific states. This leads us directly to the concept of superposition, a cornerstone of quantum mechanics. Superposition describes the ability of a quantum system to exist in multiple states simultaneously until it is measured. Imagine a quantum coin that is both heads and tails at the same time. It is not one or the other, but a combination of both possibilities existing in a probabilistic haze. Only when you look at it, when you force a measurement, does it decide to be either heads or tails. In the context of the double-slit experiment, the electron is in a superposition of going through the left slit and going through the right slit until its path is observed. This isn't merely a lack of information on our part, it is a fundamental property of the quantum entity itself. The electron truly is, in a very real sense, exploring all potential realities until a specific interaction forces it to commit to one. This inherent uncertainty is not a flaw in the theory, but a defining characteristic of the micro-world. It means that the fundamental nature of reality is probabilistic rather than deterministic. For us living in the macro world, this seems counterintuitive, almost like magic. But for the tiny constituents of the universe, it is simply how things are. This profound insight, first grappled with by pioneers like Werner Heisenberg and Erwin Schrödinger, forever changed our understanding of existence. It suggests that the reality we experience with its distinct objects and clear events is merely one of many potential realities that could have unfolded. And when we contemplate this, the idea that the very fabric of our being is constructed from particles that exist in such a fluid, uncertain state, it can evoke a profound sense of true wonder. This notion of superposition is not just a theoretical curiosity. It is a mathematical necessity within the framework of quantum theory. Particles are not simply tiny billiard balls. They are described by wave functions, which are mathematical expressions that encapsulate all the possible states a particle can be in, along with the probabilities of finding it in each of those states. It's like a whisper of all potential futures, all existing simultaneously until the moment of observation. Erwin Schrödinger famously illustrated this paradox with his thought experiment involving a cat in a sealed box, simultaneously alive and dead until the box is opened. While a macroscopic cat never truly exists in such a state, the experiment highlights the bizarre consequences of applying quantum rules to our everyday world and emphasizes the difficulty in reconciling the quantum and classical realms. It serves as a stark reminder that our common sense, honed by interactions with large objects, is simply inadequate for grasping the nuanced behavior of the very small. Furthermore, this quantum weirdness extends beyond individual particles. The entire universe, at its most fundamental level, can be thought of as a collection of quantum fields. These fields are not empty space, but rather energetic entities that permeate everything. Particles, in this view, are not distinct little entities, but rather localized excitations or ripples within these fields. An electron is a ripple in the electron field, A photon is a ripple in the electromagnetic field, and so on. This perspective, known as quantum field theory, provides a more complete and elegant description of the subatomic world. It implies that even in what we perceive as empty vacuum, these fields are constantly fluctuating, giving rise to virtual particles that momentarily pop into existence and then vanish, too fleeting to be directly observed, but leaving measurable effects. This constant, restless activity in the vacuum of space underscores that nothingness is far from inert. It is a vibrant, bubbling cauldron of potential. The implications for our understanding of reality are vast. If everything is fundamentally probabilistic, if particles only assume a definite state upon measurement, then the very foundation of what we consider real shifts. It suggests that the objective reality we perceive is not entirely independent of our interaction with it. This isn't to say that the moon isn't there when no one is looking, a common misconception. Rather, it means that its constituent particles exist in a spectrum of possibilities until they interact with something, or until information about them is obtained. The universe, in a sense, is a grand, unfolding story where the details are filled in as events transpire, rather than a fixed tapestry already completed. This profound concept has led to various interpretations of quantum mechanics, each attempting to make sense of this inherent strangeness. From the Copenhagen interpretation, which posits that the wave function simply collapses, to the many worlds interpretation, which suggests that every quantum measurement causes the universe to split into multiple parallel realities, each representing a different possible outcome. While these interpretations offer different frameworks, they all agree on the observational facts. The quantum world is fundamentally non-classical, unpredictable in its precise outcomes, and deeply probabilistic. Consider the precision required for our modern technologies. Lasers, semiconductors, even the very digital devices through which you are listening to this. All of these rely on our understanding and manipulation of quantum phenomena, the stability of atoms, the way chemical bonds form, the very existence of matter as we know it, are all governed by these peculiar quantum rules. Without the Pauli exclusion principle, for instance, which states that no two identical quantum particles can occupy the same quantum state simultaneously, all electrons would collapse into the lowest energy level, and atoms would cease to have structure, making chemistry and life impossible. So, while quantum mechanics might seem abstract and distant, its principles are intimately woven into the fabric of our everyday existence, silently underpinning the stability and diversity of the world around us. It is this intricate dance of probabilities and interactions that allows for the emergence of complex structures, from the simplest hydrogen atom to the intricate neural networks within your own brain. And as we settle into the quiet contemplation of this micro-world, we might find a peculiar comfort in its inherent uncertainty. Just as the universe at large is a vast expanse of unknown possibilities, so too are the smallest components of reality a testament to the fact that existence is far richer and more nuanced than our direct senses reveal. The idea that everything around us, and indeed within us, is a continuous interplay of probabilities, constantly shifting and coalescing, invites us to release the need for absolute certainty and embrace the quiet mystery of being. Perhaps in understanding the fluid nature of reality at its core, we can find a deeper sense of peace, knowing that our own existence, with its myriad choices and paths, is a beautiful echo of the quantum dance that underpins everything. The strange dance of quantum particles, where states remain undefined until measured, leads us to yet another profound and perhaps even more perplexing phenomenon: quantum entanglement. If the idea of a particle existing in multiple places at once feels counterintuitive, then entanglement will stretch our understanding of reality even further. Imagine two particles, perhaps two photons or two electrons, that interact in a specific way. After this interaction, they become intrinsically linked, or entangled. What this means is that their fates are intertwined, no matter how far apart they are separated in space. If you measure a property of one entangled particle, such as its spin or polarization, you instantly know the corresponding property of the other particle, even if it is light years away. This connection appears to happen instantaneously, seemingly defying the cosmic speed limit set by Albert Einstein's theory of relativity. Einstein himself, along with his colleagues Boris Podolsky and Nathan Rosen, found this concept so unsettling that they famously dubbed it spooky action at a distance. They believed it pointed to a fundamental incompleteness in quantum mechanics, suggesting that there must be hidden variables, some underlying information that predetermines the outcomes of these measurements, thus preserving classical realism and locality. However, a brilliant physicist named John Stuart Bell later formulated a theorem that provided a way to experimentally test whether such hidden variables could truly explain entanglement. Subsequent experiments, notably those by Alain Aspect and his team in the 1980s, conclusively demonstrated that the correlations observed between entangled particles are stronger than any classical theory, allowing for local hidden variables, could explain. The spooky action, it turns out, is real. It is a fundamental feature of the quantum universe, not an illusion or a gap in our knowledge. This profound interconnectedness, where particles share a common destiny irrespective of spatial separation, has no analog in our everyday world. There is no classical way to explain how two objects could instantly communicate their states without any physical interaction or signal passing between them. It compels us to rethink the very nature of reality, suggesting that at the deepest level, the universe is not merely a collection of isolated particles, but a vast, interconnected web of quantum relationships. This is not about information traveling faster than light. Rather, the particles are part of a single, unified quantum system. Their individual properties are not determined until measured, and that measurement instantly defines the state of both. This seemingly magical link is not used for transmitting classical information faster than light, but it opens doors to revolutionary technologies such as quantum communication, offering potentially unbreakable encryption, and quantum computing, where qubits, quantum bits, can leverage both superposition and entanglement to perform calculations far beyond the capabilities of classical computers. Building on this, the quantum world also presents us with the astonishing phenomenon of quantum tunneling. In classical physics, if a ball doesn't have enough energy to roll over a hill, it simply won't make it to the other side. It will roll back down. Barriers are absolute. But at the quantum scale, particles can, with a certain probability, tunnel right through an energy barrier, even if they do not possess sufficient energy to overcome it classically. It is as if they briefly borrow energy from the vacuum, or perhaps in their wave-like form, their probability wave simply extends through the barrier. While the probability of any single particle tunneling might be small, for countless particles, it becomes a regular occurrence. This seemingly impossible feat is not merely theoretical. It is a well-established quantum effect with profound implications. Quantum tunneling is, in fact, essential for life as we know it. Consider the Sun and other stars. Their immense energy comes from nuclear fusion, where hydrogen nuclei fuse to form helium. However, atomic nuclei, being positively charged, naturally repel each other due to the electromagnetic force. Classically, the temperatures and pressures in the Sun's core are not nearly high enough for protons to overcome this electrostatic repulsion and fuse. But thanks to quantum tunneling, a small fraction of these protons can effectively tunnel through this repulsive barrier, allowing fusion to occur. Without this quantum phenomenon, the Sun would not shine, and the universe would be a very different, much colder, and indeed, lifeless place. Beyond stellar processes, quantum tunneling is harnessed in technologies like scanning tunneling microscopes, which can image individual atoms by exploiting the tunneling of electrons, and it explains radioactive decay, where particles spontaneously tunnel out of unstable atomic nuclei. It is a quiet, invisible process, yet its consequences are immense and deeply woven into the fabric of the cosmos. And as we delve deeper into these strange behaviors, we encounter another fundamental principle that underpins the quantum realm: Werner Heisenberg's uncertainty principle. This principle states that there are certain pairs of properties of a quantum particle, such as its position and its momentum, that cannot both be known with perfect precision simultaneously. The more precisely you measure one, the less precisely you can know the other. This is not a limitation of our measuring instruments, nor a matter of clumsy observation disturbing the system, though that does happen. Rather, it is an inherent, irreducible fuzziness built into the very nature of reality at its most fundamental level. It's as if the universe itself has a built-in limit to what can be known about its smallest constituents. Imagine trying to precisely locate a ripple on a pond while also knowing its exact direction and speed. By trying to pinpoint its position, you disturb its motion. By trying to define its motion, you lose its precise location. This principle extends to other pairs of complementary properties, such as energy and time. A particle can briefly borrow energy from the vacuum as long as it pays it back within a very short time. The shorter the time interval, the greater the amount of energy that can be borrowed. This allows for the fleeting existence of those virtual particles we discussed earlier, constantly popping in and out of existence in seemingly empty space. The uncertainty principle paints a picture of a universe that is not a perfectly defined machine, but rather a dynamic, subtly blurred tapestry of probabilities. It means that at the very root of all existence, there is an irreducible element of chance, an inherent unpredictability that defies deterministic prediction. This profound insight forces us to reconsider our classical notions of cause and effect, suggesting that some events are truly random, not just due to our lack of information. And when we reflect on this, the idea that the universe, even at its core, holds a graceful inherent uncertainty. It can bring a quiet sense of wonder, allowing us to find peace in the unknown, much like drifting into a tranquil sleep. We have journeyed through the realm where particles exist in multiple states and are mysteriously linked across vast distances. Now, let us consider the deeper tapestry from which these phenomena emerge, the concept of quantum fields. Our everyday perception often leads us to imagine particles as tiny, discrete balls, like miniature marbles. However, modern physics, particularly quantum field theory, offers a more profound and elegant perspective. It suggests that the universe is not fundamentally made of particles, but rather of fields that permeate all of space and time. These fields are not static or empty. Instead, they are dynamic, vibrant entities, constantly fluctuating even in what appears to be a perfect vacuum. Particles, in this view, are not fundamental objects themselves, but rather localized excitations or tiny ripples in these underlying quantum fields. Imagine a vast, calm ocean. A particle is not a distinct drop of water, but a momentary wave, a disturbance that travels across its surface. Every type of fundamental particle we know, electrons, photons, quarks, corresponds to a specific quantum field. An electron, for instance, is an excitation in the electron field, and a photon is a quantum of the electromagnetic field. This perspective allows us to reconcile the wave-particle duality we discussed, as particles are both wave-like, as fields, and particle-like, as localized excitations. This grand framework of quantum fields forms the bedrock of what we call the Standard Model of particle physics. The Standard Model is our most successful theory describing the fundamental particles and forces that govern the universe, excluding gravity. It categorizes matter particles, known as fermions, such as quarks and leptons, which include electrons and neutrinos. These are the building blocks of all ordinary matter. Then there are force-carrying particles called bosons, which mediate the fundamental interactions. For example, photons carry the electromagnetic force, which is responsible for light, electricity, and magnetism, and holds atoms together. Gluons carry the strong nuclear force, binding quarks together within protons and neutrons, and holding atomic nuclei intact. The W and Z bosons mediate the weak nuclear force, responsible for radioactive decay and nuclear fusion processes that power stars. This model is a triumph of human intellect, painstakingly developed over decades by countless scientists, uniting seemingly disparate phenomena under a single, coherent set of mathematical principles. It tells us that the universe, at its deepest level, is a symphony of interacting fields, a continuous hum of potentiality from which all reality emerges. Within this intricate standard model, one particular field holds a unique and crucial role in shaping the universe as we perceive it: the Higgs field. For many years, physicists grappled with a perplexing question: why do some fundamental particles have mass, while others, like the photon, appear to be massless? The answer, according to the Standard Model, lies with the Higgs field, an invisible energy field that pervades all of space. Imagine walking through a swimming pool filled with treacle or thick syrup. Some particles, those that interact strongly with the Higgs field, experience a greater drag or resistance as they move through it, much like walking through treacle. This resistance is what we perceive as mass. Particles that interact weakly with the Higgs field acquire less mass, and those that do not interact with it at all, like photons, remain massless, gliding unimpeded through the cosmic treacle. This interaction with the Higgs field is not a force in the traditional sense, but a fundamental property of how particles acquire their inertia, their resistance to changes in motion. The existence of the Higgs field was a theoretical prediction for decades, a missing piece in the Standard Model. It was hypothesized by Peter Higgs and several other physicists in the 1960s. The experimental confirmation of the Higgs boson, the particle associated with the Higgs field, at the Large Hadron Collider in 2012, was a monumental achievement in physics, a crowning moment that validated the Standard Model and deepened our understanding of the origin of mass. This discovery revealed that mass is not an inherent quality of particles, but rather a consequence of their interaction with this ubiquitous, all-pervading field. It means that the very solidity and substance of everything around us, including our own bodies, is a manifestation of these subtle, constant interactions with the Higgs field. We are, in a very real sense, continually immersed in this field, and its presence defines one of the most fundamental properties of our physical existence. This elegant mechanism provides a gentle yet profound explanation for why the universe has structure, why stars and galaxies can form, and why we, as beings with mass, can exist within it. As we contemplate these quantum fields and their intricate interactions, a natural question arises. If the micro-world is so strange, filled with superposition and entanglement, why do we not observe these phenomena in our everyday macroscopic lives? Why does the moon appear to be in a definite location, rather than a blur of possibilities? The answer lies in a process known as quantum decoherence. Decoherence is the mechanism by which quantum systems lose their quantum properties and begin to behave classically. It occurs when a quantum system interacts with its environment. At the microscopic scale, isolated particles can maintain their delicate quantum states, like superposition, for a fleeting moment. However, in our macroscopic world, systems are constantly interacting with an immense number of particles in their surroundings: air molecules, photons, thermal vibrations. Each of these interactions acts as a measurement, however indirect, forcing the quantum system to collapse from a superposition of states into a single, definite, classical state. Imagine our quantum coin simultaneously heads and tails. If it is perfectly isolated, it remains in this superposition. But if it interacts with even a single air molecule, that interaction essentially observes it, forcing it to choose either heads or tails. The more complex a system and the more it interacts with its environment, the faster decoherence occurs. For something as large as a human being, with countless atoms constantly interacting with the environment, decoherence happens almost instantaneously, making it impossible to observe ourselves in a quantum superposition. This continuous interaction with the environment effectively erases the quantum weirdness, smoothing out the probabilities into the distinct classical reality we experience. So, the classical world is not separate from the quantum world. It emerges from it through this constant process of decoherence. It is a beautiful reconciliation, explaining how the baffling rules of the micro-world give rise to the reassuringly stable and predictable macro-world we inhabit. It's a gentle reminder that the universe has a way of organizing itself, allowing for both profound mystery at its core and tangible reality on its surface. We have journeyed through the realms of wave-particle duality, the perplexing double-slit experiment, and the profound interconnectedness of entanglement, all emerging from the vibrant tapestry of quantum fields. Now, let us consider the subtle yet immensely powerful energy inherent in what we often perceive as empty space. In classical physics, a vacuum is simply nothingness, a void devoid of matter and energy. However, quantum mechanics paints a far more dynamic picture. Even in the absence of any particles or radiation, the quantum fields we discussed earlier are never truly at rest. They are constantly fluctuating, bubbling with activity, giving rise to what are known as virtual particles. These particles, pairs of matter and antimatter, spontaneously pop into existence for an infinitesimally brief moment, only to annihilate each other and vanish back into the quantum foam. They are too fleeting to be directly observed, yet their transient existence has real, measurable effects, such as the Casimir effect, where two uncharged parallel metal plates placed very close together in a vacuum will actually experience a slight attractive force. This force arises from the subtle differences in the quantum fluctuations between the plates compared to those outside, demonstrating that empty space possesses an intrinsic energy, often referred to as vacuum energy. This vacuum energy is not merely a curiosity of the micro-world. Its implications extend to the largest scales of the cosmos. Scientists believe that this inherent energy of space might be intimately connected to the phenomenon of dark energy, the mysterious force responsible for the accelerating expansion of our universe. The cosmological constant, a term originally introduced by Albert Einstein into his equations of general relativity, but later famously retracted, has found a potential modern interpretation as a manifestation of this vacuum energy. While there is still a significant discrepancy between the theoretical predictions of vacuum energy and the observed strength of dark energy, the very idea suggests a profound link between the quantum realm and the large-scale structure and evolution of the universe. It hints that the expansive cosmic ballet we observe, with galaxies drifting ever further apart, might be gently orchestrated by the ceaseless, imperceptible activity of the quantum vacuum itself. The universe, then, is not expanding into a void of nothingness, but rather the nothingness itself is expanding, fueled by its own latent quantum energy, a concept that invites a deep, quiet contemplation of existence. This ability of quantum particles to exist in multiple states simultaneously and to be profoundly linked through entanglement is not merely a theoretical construct for physicists to ponder. It is being actively harnessed and engineered to develop revolutionary new technologies, most notably in the field of quantum computing. Unlike classical computers, which store information in bits that can only be either a 0 or a 1, quantum computers utilize quantum bits, or qubits. A qubit, thanks to the principle of superposition, can be both a 0 and a 1 simultaneously. This allows a quantum computer to process vast amounts of information in parallel, exploring multiple possibilities at once. Furthermore, when qubits are entangled, their fates become linked, meaning that the state of one instantly influences the state of others, regardless of distance. This entanglement allows for incredibly complex calculations and correlations between qubits that are impossible for classical systems to replicate. Imagine a symphony where each musician can play all notes at once and their instruments are mysteriously linked, instantly resonating with each other. This is the power that superposition and entanglement bring to quantum computation. While still in its nascent stages, quantum computing promises to revolutionize fields ranging from medicine and material science to cryptography and artificial intelligence. For instance, designing new drugs or materials often involves simulating complex molecular interactions, a task that quickly overwhelms even the most powerful classical supercomputers. Quantum computers, with their ability to model quantum phenomena directly, could unlock breakthroughs in these areas, allowing us to engineer substances with unprecedented properties or develop highly targeted therapies. In cryptography, quantum algorithms could break many of the encryption methods currently used to secure our digital communications, while simultaneously offering new, quantum-safe encryption techniques that are theoretically unbreakable. The development of quantum computers is a testament to the profound practical implications of understanding the subtle laws governing the microworld, transforming what once seemed like abstract philosophical puzzles into tools that could reshape our future in profound, yet often quietly unfolding ways. Yet, despite these incredible advancements and applications, the quantum world continues to present us with fundamental puzzles, perhaps none more enduring than the measurement problem. We have already touched upon how observation causes the collapse of a quantum system's wave function, forcing it into a definite state. But what precisely constitutes a measurement? And does the act of observation imply a role for consciousness? While most physicists agree that any irreversible interaction with the environment, even by an inanimate detector, is sufficient to cause decoherence and collapse, the deeper philosophical questions persist. Different interpretations of quantum mechanics offer varying perspectives, each attempting to provide a coherent narrative for this perplexing aspect of reality. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, suggests that quantum systems simply do not possess definite properties until they are measured, and that measurement fundamentally alters the system. The many worlds interpretation, on the other hand, proposes with all outcomes being equally real. These are not just scientific theories, but profound reflections on the nature of reality itself. These ongoing debates highlight that even with our advanced understanding, the quantum realm retains an intrinsic mystery. It reminds us that our models and theories, while incredibly powerful and predictive, are still human constructs attempting to describe a reality that may ultimately transcend our intuitive grasp. The quest to fully comprehend the measurement problem and to reconcile quantum mechanics with the other great pillar of modern physics, general relativity, continues to drive scientific exploration. The search for a theory of quantum gravity, one that can seamlessly describe the universe at both the smallest quantum scales and the largest cosmic scales, remains one of the greatest challenges in physics. It is a testament to the boundless nature of inquiry, to the human spirit's relentless desire to understand the fundamental truths of existence. And perhaps in this ongoing journey of discovery, in the humble acceptance of what remains unknown, we find a tranquil beauty, a profound sense of awe that allows our minds to drift gently into the quiet expanse of the night, knowing that the universe holds secrets far grander than we can yet imagine, and that we are a part of this unfolding mystery. The profound mysteries of quantum mechanics, from the unsettling implications of the double-slit experiment to the instantaneous connections of entanglement, often lead us to ponder the very nature of reality. Yet it is crucial to remember that despite these philosophical depths, quantum mechanics is also an extraordinarily successful scientific theory, perhaps the most precisely tested and validated theory in all of physics. It is the bedrock upon which our understanding of chemistry, material science, and modern technology is built. Two of its most triumphant formulations are quantum electrodynamics, or QED, and quantum chromodynamics, or QCD. These theories represent our deepest insights into how particles interact through two of the fundamental forces, electromagnetism and the strong nuclear force. Quantum electrodynamics, often called the jewel of physics, describes how light and matter interact. It is a quantum field theory that beautifully explains everything from how electrons orbit atomic nuclei to the intricate dance of photons being emitted and absorbed. In QED, forces are not transmitted directly, but rather mediated by the exchange of virtual particles. For instance, when two electrons repel each other, they are not simply pushing. They are exchanging virtual photons, like two skaters throwing a ball back and forth, causing them to move apart. These virtual photons exist for such an incredibly brief time that they cannot be directly observed, a consequence of Heisenberg's uncertainty principle applied to energy and time. Yet their effects are profoundly real and precisely calculable. The predictions of QED, such as the anomalous magnetic moment of the electron, match experimental observations to an astonishing 10 decimal places, making it one of the most accurate theories ever devised. This incredible precision underscores that even the most ethereal concepts of quantum mechanics are rooted in a reality that we can measure and understand, albeit one that operates beyond our classical imaginings. Moving deeper into the atomic nucleus, we encounter quantum chromodynamics, or QCD. This theory describes the strong nuclear force, which is responsible for binding quarks together to form protons and neutrons, and subsequently holding these protons and neutrons within atomic nuclei. Quarks, the fundamental constituents of protons and neutrons, possess a property called color charge, an analogy to electric charge, but with three types: red, green, and blue. Just as electric charges interact by exchanging photons, color-charged quarks interact by exchanging particles called gluons. Gluons, unlike photons, carry color charge themselves, which leads to a peculiar and powerful characteristic of the strong force. It actually gets stronger with distance. Imagine trying to pull two magnets apart, and the further you pull them, the stronger the force becomes, eventually making it impossible to separate them. This is why we never observe free quarks in isolation. They are always confined within composite particles like protons and neutrons, a phenomenon known as color confinement. QCD, with its elegant description of quarks and gluons, completes our understanding of the fundamental building blocks of ordinary matter and the forces that hold them together, a testament to the profound order within the seemingly chaotic quantum realm. These quantum theories also provide the definitive explanation for the very structure and stability of atoms, and by extension, the diversity of the chemical elements. In the classical view, electrons orbiting a nucleus should quickly spiral inward due to electromagnetic attraction, causing atoms to collapse. However, quantum mechanics reveals that electrons exist in discrete energy levels or orbitals around the nucleus. They can only occupy specific quantized energy states, much like steps on a ladder, rather than being able to exist at any arbitrary height. An electron can jump between these energy levels by absorbing or emitting a photon of a precise energy, but it cannot exist in between. This concept of quantized energy, first proposed by Niels Bohr and later refined by Erwin Schrödinger, elegantly explains why atoms are stable and why they emit and absorb light at specific wavelengths, giving each element its unique spectral fingerprint. The Pauli exclusion principle, which we touched upon earlier, further dictates that no two electrons in an atom can occupy the exact same quantum state, preventing all electrons from piling into the lowest energy level. This principle is fundamental to the formation of the periodic table, determining how electrons fill successive shells and, in turn, dictating the chemical properties of elements. It is the quantum rules that ultimately orchestrate the intricate dance of electrons, shaping the very architecture of matter and enabling the rich tapestry of chemistry that forms our world. Ultimately, the quantum world teaches us that reality is fundamentally probabilistic. While classical physics offered a deterministic view where every event is predetermined by prior conditions, quantum mechanics introduces an irreducible element of chance. We can calculate the probabilities of various outcomes for a quantum event, but we cannot predict with certainty which outcome will actually occur until a measurement is made. This probabilistic nature is not a reflection of our ignorance, but rather a deep, inherent feature of the universe at its most fundamental scale. It means that the future, in a very real sense, holds genuine openness, a myriad of possibilities waiting to coalesce into a definite reality. This can be a profound and liberating thought, reminding us that even in the grand cosmic scheme, there is room for novelty and emergent possibilities. As we drift into the quietness of the night, perhaps we can embrace this quantum truth, that our own lives, too, are an unfolding of probabilities, a unique and beautiful journey through a universe that is both governed by fundamental laws and imbued with an astonishing inherent freedom. Let this gentle understanding of the micro-world carry you deeper into a peaceful state of rest, knowing that the smallest scales of existence hold the grandest implications for everything we perceive. Our exploration of quantum mechanics has illuminated a universe far stranger and more intricate than our classical senses could ever suggest, a world of intertwined possibilities and fundamental uncertainties. We have seen how the Standard Model brilliantly describes the electromagnetic and strong nuclear forces, and how the Higgs field bestows mass upon particles. Yet, there remains a monumental, unfinished symphony in our understanding, the reconciliation of quantum mechanics with the force of gravity. While quantum theories excel at describing the very small, Albert Einstein's theory of general relativity reigns supreme in describing gravity and the large-scale structure of the cosmos, from planets to galaxies. These two pillars of modern physics, incredibly successful within their own domains, speak different mathematical languages and offer fundamentally different pictures of reality, especially when we consider extreme conditions such as the heart of a black hole or the very first moments of the Big Bang. The challenge lies in their core assumptions. General relativity views space-time as a smooth, flexible fabric that can be warped by mass and energy, creating gravity. Quantum mechanics, on the other hand, suggests that all forces, including gravity, should be mediated by discrete particles, gravitons in this case, and that space-time itself should be quantized, existing in tiny, indivisible packets, or quanta. This fundamental incompatibility leads to problems when physicists try to combine them. When the smooth, continuous geometry of space-time from general relativity is subjected to the probabilistic, fluctuating nature of quantum fields, the equations break down, yielding nonsensical infinities. It is as if we are trying to describe the ripples on a pond, quantum mechanics, with a theory designed only for the overall shape of the lake, general relativity, or vice versa. The scales at which these theories become relevant are vastly different, yet at the universe's most extreme points, they must converge. This quest for a theory of quantum gravity is perhaps the greatest challenge facing theoretical physics today, a silent call to uncover an even deeper, more unified truth about the universe. In response to this profound challenge, physicists have developed several theoretical frameworks, each attempting to bridge this divide, to weave gravity into the quantum tapestry. Two of the most prominent approaches are string theory and loop quantum gravity. String theory, a particularly elegant and ambitious framework, proposes that the fundamental constituents of the universe are not point-like particles, but rather tiny, one-dimensional vibrating strings, unimaginably small. Different vibrational patterns of these strings correspond to different particles, including the elusive graviton. This theory requires the existence of extra spatial dimensions beyond the three we perceive, curled up so tightly that they are currently undetectable. Loop quantum gravity, on the other hand, takes a different path, attempting to quantize space-time itself. It suggests that space-time is not a smooth continuum, but is instead composed of discrete, quantifiable loops, forming a fabric that is granular at the Planck scale, an incredibly tiny scale where our familiar notions of space and time are thought to break down. These theories, while still speculative and awaiting experimental verification, offer breathtaking visions of reality, hinting that the smooth, continuous universe we inhabit might be an illusion, an emergent property of a much more fundamental, discrete quantum structure. The implications of these ideas are truly profound, suggesting that space-time itself might not be a fundamental entity, but rather an emergent phenomenon. Just as the seemingly solid objects of our everyday world emerge from the probabilistic dance of quantum particles, so too might the smooth expanse of space and the relentless flow of time arise from a deeper, granular quantum substratum. Imagine looking at a photograph. From a distance, it appears as a continuous image, but zoom in close enough, and you reveal the discrete pixels that compose it. In a similar vein, the universe, at the most fundamental level, might be a network of quantum pixels of space-time, each carrying information about its geometry and connections. Our everyday experience of space as continuous and time as flowing smoothly would then be an approximation, valid at large scales, but breaking down at the smallest, most fundamental quantum limits. This perspective offers a serene, yet radical understanding that the very stage upon which the cosmic drama unfolds might itself be a participant in the quantum dance, constantly fluctuating and rearranging its scales far beyond our direct perception. This concept of emergent space-time also brings us to the Planck scale, a set of fundamental units derived from universal physical constants: the speed of light, Planck's constant, and the gravitational constant. At the Planck length, which is an unimaginably tiny 1.6 times 10 to the power of minus 35 meters, and the Planck time, an equally minuscule 5.4 times 10 to the power of minus 44 seconds, our current laws of physics begin to lose their meaning. This is where the quantum nature of gravity is expected to become dominant, where space-time itself is thought to become foamy and discontinuous. Below these scales, the very notions of where and when, as we understand them, may cease to apply. It is a boundary of human comprehension, a frontier where our current scientific tools and theories reach their limits. This ultimate fuzziness at the deepest level of reality can be a source of quiet contemplation, reminding us that the universe holds mysteries that transcend our immediate grasp, and that true understanding often lies beyond the veil of our everyday experience. Reflecting on these grand cosmic puzzles, on the quest to unify the very small with the very large, we can find a profound sense of our own place within this magnificent and mysterious unfolding. The knowledge that the space-time we navigate daily, the gravity that holds us to the Earth, might ultimately be an emergent property of a deeper quantum reality, invites us to view our existence with renewed awe. We are living, breathing configurations of quantum fields, experiencing an emergent classical reality, all while being part of a universe that is still revealing its most fundamental secrets. This ongoing journey of discovery, this gentle push against the boundaries of the known, is a testament to the enduring human spirit of inquiry. May these thoughts about the profound and elegant mysteries of the quantum world and our ceaseless quest to understand them bring a quiet sense of wonder and deepen your path towards a tranquil, restful sleep. The journey through the quantum realm has illuminated a universe of profound strangeness, where particles exist in states of superposition and are linked by entanglement, defying our classical intuitions. We've seen the intricate workings of quantum fields, giving rise to matter and forces, and the monumental quest to unify these microscopic laws with the cosmic grandeur of gravity. This ongoing search, particularly at the unimaginably tiny Planck scale, forces us to confront not just the limits of our theories, but perhaps the very nature of reality itself. If space-time is emergent, if particles are but ripples in fields, what then is the ultimate fabric of existence? This question leads us to ponder the role of information in the quantum universe, a concept that deepens the mystery and invites a quiet contemplation of what it means for anything to truly be. In the quantum world, information is not merely a collection of facts. It is a fundamental property, a conserved quantity. Unlike in classical physics, where information can be easily lost or destroyed, quantum mechanics suggests that information is never truly annihilated, only scrambled or transformed. This principle is famously highlighted by the black hole information paradox, a perplexing puzzle that arises when trying to reconcile quantum mechanics with general relativity. When matter falls into a black hole, it seems to vanish, taking all its quantum information with it. However, if information cannot be destroyed, then it must somehow be preserved, perhaps encoded on the event horizon, the black hole's boundary, or radiated away in a subtle form. While the exact resolution to this paradox remains a subject of intense research and debate, it underscores the profound importance of information in the quantum universe. It suggests that even the most extreme cosmic phenomena must adhere to the conservation of quantum information, implying a deeper, more resilient underlying order than we might initially perceive. This idea that information in its essence is eternal can bring a quiet sense of reassurance, like an echo of permanence within the ceaseless flow of change. It reshapes our understanding of what constitutes a fundamental building block of reality, moving beyond mere particles and forces to a realm where information itself plays a pivotal role, perhaps even as the ultimate substrate of all that exists. This brings us back to the enigmatic role of observation and the measurement problem, a concept that continues to challenge our intuitive grasp of reality. As we explored, a quantum system exists in a superposition of all possible states until it is measured, at which point it collapses into a single, definite outcome. This implies that the act of interacting with a system fundamentally influences its reality. It's not that we are simply passively observing an already fixed universe. Rather, our interactions, even at an unconscious level, play a role in defining the reality that emerges. This is a subtle yet profound distinction. The universe, at its deepest quantum level, is not a predetermined tapestry, but a canvas of potential, where the strokes are made through interaction. This shift from a purely objective, independent reality to one that is, in some sense, participatory, is one of the most radical departures from classical thought. It suggests a delicate interplay between observer and observed, a quiet dance of definition where possibilities condense into concrete events. To truly grasp this, one must let go of the ingrained notion of a fully formed, independent reality awaiting our discovery, and instead embrace a more fluid, interactive picture of existence. It is a profound invitation to consider our own role, however small, in the continuous unfolding of the cosmos. The ongoing scientific discourse surrounding the interpretations of quantum mechanics further highlights this deep philosophical challenge. The Copenhagen interpretation, perhaps the most widely accepted, emphasizes the probabilistic nature of quantum reality and the role of measurement in collapsing the wave function, without delving into what happens to the other possibilities. It suggests that asking what a particle is doing when not observed is simply not a meaningful question. Posits branch outcome. In this view, all possibilities are realized, but in separate, inaccessible universes. Then there are other interpretations, like pilot wave theory, which suggests that particles always have definite positions but are guided by an invisible quantum wave, or objective collapse theories, which propose that wave functions collapse spontaneously without the need for an observer when a certain physical threshold is met. The very existence of these diverse yet equally valid interpretations reminds us that even at the forefront of scientific discovery, there is ample room for profound philosophical contemplation. It is a gentle invitation to explore the boundaries of what we consider knowable, fostering a sense of humble wonder at the universe's capacity for mystery. and encouraging a peaceful acceptance of the multifaceted nature of truth. These deeply strange quantum phenomena, while seemingly confined to the subatomic world, ultimately underpin the stability and existence of everything we experience. The very fact that atoms hold together, that chemical reactions occur, that light interacts with matter in predictable ways, all depend on these quantum rules. Our bodies, the air we breathe, the ground beneath our feet, are all intricate arrangements of quantum particles behaving according to these probabilistic laws. The delicate balance between the inherent uncertainty of the quantum realm and the emergent stability of the macroscopic world is what allows for complexity, for life, and for consciousness to arise. It is a testament to the universe's exquisite design that such a fluid and probabilistic foundation can give rise to the structured and seemingly solid reality we inhabit. This grand coherence, emerging from such fundamental strangeness, can inspire a deep sense of peace, a quiet appreciation for the hidden mechanisms that allow us to simply be. It suggests that even our most profound experiences, our thoughts, and our very awareness are intricate patterns woven from the quantum fabric, an astonishing dance of energy and information that continually shapes our perceived reality. And so, as we reflect on these profound quantum insights, we are reminded that our understanding of the universe is an ever-evolving journey, a continuous unfolding of deeper truths. The micro-world, far from being a simple miniature version of our everyday experience, reveals a reality that is fundamentally different, more dynamic, and more mysterious. It teaches us about the interconnectedness of all things, the inherent role of observation, and the probabilistic nature of existence itself. This knowledge, rather than being unsettling, can bring a quiet sense of expansion, an awareness that we are part of a cosmic dance far grander and more intricate than we often realize. In this deep contemplation, we can find a gentle release, allowing our minds to settle into a state of tranquil wonder, knowing that the universe, in all its quantum glory, holds us gently within its vast and truly profound sleep. This intricate dance has led us to ponder the very nature of information and the emergent quality of space-time itself, particularly at the unimaginably tiny Planck scale. Yet, even as we consider these grand, abstract concepts, it is important to remember that the quantum world is not just about distant black holes or theoretical strings. Its strange rules govern the very fabric of our immediate reality, influencing even the most seemingly mundane aspects of our existence, including the solidity of the ground beneath our feet and the touch of our own hands. One of the most surprising revelations from quantum mechanics is the profound emptiness within what we perceive as solid matter. Our everyday intuition tells us that a table, a book, or even our own bodies are dense, tangible things, full of stuff. But when we delve down to the atomic scale, this intuition completely breaks down. An atom, the fundamental building block of all matter, is actually almost entirely empty space. Its tiny, incredibly dense nucleus composed of protons and neutrons is surrounded by a cloud of electrons. The scale of this emptiness is truly staggering. If an atom's nucleus were the size of a small pea placed at the center of a football stadium, the electron cloud would extend to the stadium's outermost walls. And everything in between would be nothing but vacuum. The electrons themselves are not tiny planets orbiting the nucleus. They exist as diffuse probability clouds, smeared out across this vast emptiness. So, when you hold an object in your hand, what you are fundamentally holding is mostly space, structured and held together by invisible forces and the peculiar rules of the quantum realm. This realization can be deeply calming, offering a new perspective on the illusion of solidity and the ephemeral nature of all physical forms. What then gives matter its apparent solidity? Why don't our hands pass right through a table, or why don't we fall through the floor? The answer lies in the electromagnetic force and a crucial quantum principle, the Pauli exclusion principle. At the atomic level, the outer layers of atoms are populated by electrons, which carry a negative electric charge. When two atoms come close to each other, their electron clouds strongly repel each other due to this like charge repulsion. This electromagnetic pushback is what we consciously perceive as the sensation of touch or solidity. There is no true contact in the classical sense, no merging of matter. Rather, it is a dance of repulsion, an invisible cushion of electric fields keeping atoms from overlapping. Furthermore, the Pauli exclusion principle, formulated by Wolfgang Pauli, states that no two identical quantum particles, particularly fermions like electrons, can occupy the exact same quantum state at the same time. This fundamental rule is not just a statistical oddity. It is a profound law built into the very fabric of the universe that dictates matter's structure. It is what prevents all electrons from collapsing into the lowest energy level around an atom, ensuring that atoms maintain their distinct shells and that different elements exhibit unique chemical properties. Without this principle, all matter would simply collapse into an undifferentiated, dense blob, and the complexity of the universe, including life itself, would be impossible. So, the solidity we feel is a direct consequence of these quantum rules, a testament to the elegant order emerging from the chaotic quantum dance. The very emptiness of space, even the vacuum between stars and galaxies, is also far from truly empty, as we've noted. It is a vibrant, restless sea of quantum fields, constantly giving rise to virtual particles that flicker into existence and vanish. This zero-point energy, or vacuum energy, suggests that the lowest possible energy state of space is not zero, but rather a teeming, dynamic realm of potential. This continuous effervescence of the quantum vacuum has profound implications, extending to the accelerating expansion of the universe itself, driven by what we call dark energy. While the precise connection between vacuum energy and dark energy is still one of the greatest unsolved puzzles in physics, the underlying idea is that the very void of space possesses an intrinsic energy that can exert a repulsive force, gently stretching the cosmos apart. This means that even the most seemingly empty regions of the universe are alive with activity, a constant, subtle hum of creation and annihilation that shapes the grand cosmic ballet. It is a quiet, powerful reminder that the universe is always in motion, always evolving, even in its deepest, most tranquil expanses. The intricate interplay of these quantum phenomena, wave-particle duality, superposition, entanglement, decoherence, the vacuum energy, and the fundamental forces, ultimately gives rise to the complex, diverse, and dynamic universe we inhabit. From the fusion reactions that power stars enabled by quantum tunneling to the intricate chemical bonds that form molecules and ultimately life, the quantum rules are the unseen architects of reality. Every atom in your body, every thought in your mind, every sensory experience is a manifestation of these deep, probabilistic processes. This profound interconnectedness, where the smallest ripples in quantum fields give rise to the grand structures of the cosmos, can evoke a deep sense of belonging. We are not mere spectators in this quantum universe. We are integral participants, woven from its very fabric, continuously engaged in its intricate dance. As we gently conclude our reflections on how the micro-world works, let us carry this sense of wonder and interconnectedness into the quietude of the night. The universe, at its smallest scales, is a place of ceaseless activity, profound mystery, and elegant laws, a realm where intuition gives way to the astonishing beauty of quantum reality. May the understanding of this intricate, probabilistic dance, from the emptiness within atoms to the vibrant energy of the vacuum, bring a deep and tranquil peace to your mind. Fall asleep with the awareness that you are a complex, miraculous expression of these fundamental cosmic principles, a brief but brilliant pattern in the infinite tapestry of existence. Good night. Our As we consider the intricate patterns woven from the quantum fabric that compose our very being, a fascinating and highly speculative frontier of physics emerges: the realm of quantum biology. This nascent field explores whether quantum phenomena, typically thought to occur only in isolated, extremely cold or very small systems, might actually play a crucial role in the warm, noisy, and complex environment of living organisms. It challenges the long-held assumption that biological systems are too large and too messy for delicate quantum effects, like superposition and entanglement, to persist. Yet, evidence is slowly mounting that nature might have found ingenious ways to harness these quantum quirks for essential biological processes. Imagine for a moment the subtle whispers of quantum mechanics guiding the fundamental operations of life itself, a profound and elegant possibility that could redefine our understanding of biology. One of the most compelling examples comes from photosynthesis, the process by which plants convert sunlight into energy. Early stages of photosynthesis involve light-harvesting proteins that capture photons and efficiently transfer their energy to reaction centers. Research suggests that this energy transfer might be guided by quantum coherence, a state similar to superposition where energy can explore multiple pathways simultaneously, essentially finding the most efficient route through a complex molecular network. This quantum shortcut allows plants to achieve near-perfect efficiency, a feat that would be impossible if energy transfer relied solely on classical random diffusion. Another intriguing area is the navigation of migratory birds. Some theories propose that birds use Earth's magnetic field to orient themselves, and that this magnetic sense could involve quantum entanglement within specific molecules in their eyes. The entangled electrons in these molecules might react differently to subtle variations in the magnetic field, providing the birds with a quantum compass. These are not definitive proofs, but compelling hints that life, at its most fundamental level, might be leveraging the strange rules of the quantum world to its advantage, quietly operating at the very edge of what we understand about physics and biology. The potential for quantum effects to influence even higher-level biological functions, such as consciousness itself, remains a deeply controversial and highly speculative area. Some pioneering thinkers, like Roger Penrose and Stuart Hameroff, have proposed that consciousness might not be a purely classical emergent property of complex neural networks, but rather could involve quantum processes occurring within the microtubules of brain neurons. This orchestrated objective reduction theory suggests that consciousness arises from quantum coherence and its subsequent collapse, linking the subjective experience of awareness directly to the fundamental uncertainty of the quantum realm. While this idea is far from mainstream acceptance and faces significant scientific hurdles, it represents a bold attempt to bridge the explanatory gap between the physical brain and the phenomenon of consciousness, offering a vision where our very thoughts and perceptions are intricately woven into the quantum tapestry. It asks us to consider whether the subjective inner world we inhabit might be a direct reflection of the universe's most profound and subtle mechanics, inviting a deep personal contemplation of our own existence as a quantum phenomenon. The very act of observing, of forming a thought, might be a tiny echo of the universe's own quantum choices, a continuous process of reality solidifying from a sea of possibilities. Beyond biology, the practical applications of quantum mechanics continue to expand, reshaping our technological landscape in ways that were once considered science fiction. We've already mentioned quantum computing, but consider the everyday technologies that rely on these principles. Lasers, which power everything from fiber optic communication to medical surgery, operate by precisely controlling the quantum transitions of electrons within atoms. Semiconductor devices, the very heart of all modern electronics, from your smartphone to supercomputers, function because of our ability to manipulate the quantum behavior of electrons in materials. Magnetic resonance imaging, or MRI, a vital diagnostic tool in medicine, harnesses the quantum property of nuclear spin to create detailed images of the human body. These technologies, now commonplace, are powerful testaments to the predictive power and tangible reality of quantum mechanics. They demonstrate that even if the quantum world feels abstract or counterintuitive, its rules are rigorously applied and thoroughly understood enough to build the foundations of our modern world. It is a quiet miracle of engineering, transforming the elusive principles of the very small into tools that profoundly shape our daily lives, a harmonious blend of abstract theory and concrete utility. Yet, despite these incredible successes, the philosophical implications of quantum mechanics continue to provoke deep thought. The measurement problem, the question of when and how a quantum superposition collapses into a definite state, remains an area of active debate and interpretation. Some physicists lean towards the idea that the universe simply chooses an outcome when a measurement occurs, while others, following the many worlds interpretation, believe that all possible outcomes are realized in branching parallel universes. These interpretations are not mere academic curiosities. They challenge our most fundamental assumptions about the nature of reality, causality, and even the role of consciousness in the cosmos. There is no single, universally accepted answer, and perhaps there never will be one that fully satisfies our classical intuition. This ongoing mystery, this graceful ambiguity at the heart of existence, can be a source of profound peace rather than anxiety. It invites us to embrace the unknown, to find beauty in the questions that remain unanswered, and to accept that the universe is far richer in its possibilities than any single fixed reality could ever be. This grand tapestry of quantum phenomena, from the vibrating strings of theoretical physics to the quantum whispers within living cells, constantly reshapes our understanding of ourselves and our place in the cosmos. We are, quite literally, made of probabilities, existing in a reality that is both profoundly structured and inherently fluid. The gentle hum of virtual particles in the vacuum, the entangled dance of distant photons, and the subtle quantum coherence within our own biological processes are all part of the same magnificent, interconnected story. Embracing this perspective can bring a deep sense of calm, dissolving the rigid boundaries between self and universe, between observer and observed. It encourages us to see ourselves not as separate entities, but as an integral, active part of the universe's self-organizing quantum dance. The very act of perceiving, of contemplating these ideas, is a quantum process in itself, a moment where the vastness of the cosmos is reflected in the intricate workings of our own minds. This realization that our internal world mirrors the external quantum reality can be a source of profound serenity, a profound awareness of the seamless unity between the microcosm and the macrocosm. It is a reminder that even in the quietest moments, the universe is alive within us. May these deep thoughts about the intricate and wondrous world of quantum mechanics carry you into a realm of tranquil sleep. Remember that the universe, at its most fundamental level, is a place of profound mystery and elegant laws, a continuous dance of possibilities from which all reality, including your own, emerges. You are, in every atom and every interaction, a part of this astonishing quantum tapestry. Fall asleep with this feeling of serene wonder and an expanded understanding of the cosmos that cradles us all. Good night.